advanced materials such as nanocrystals, nano-quasicrystals, normal quasicrystals, glasses, bulk metallic glasses, and a number of nano composites. So today we will start on the aluminum alloys and what kind of advances have taken place in aluminum alloys. If you look at the aluminum alloys per se and look at the history of it, the most conventional alloys in aluminum alloy series are aluminum copper, we all know. It's not. It's not. Okay. So the most common aluminum alloys are the aluminum copper series, we all know, particularly the duraluminum alloys, where some amount of magnesium is usually added to get the Al2 Cu Mg phase. Otherwise, if you don't add the magnesium, it's basically the Al2 Cu phase, which is called the theta phase, and has an orthorhombic structure, and we all know that this kind of a phase is very brittle. So we do what is called precipitation hardening in these alloys, aluminum copper alloys, where we solutionize these alloys at high temperature, something around 550 degrees or so, and then quench this high temperature single phase region to room temperature and do aging at various temperatures, including what is called natural aging, which is at room temperature. So when you age these aluminum copper alloys, usually you get a number of phases starting from what are called GP zones, theta double prime, theta prime, and finally the equilibrium theta phase. This is what is people call usually as the Ostwald step rule, that when you have a product phase which is an equilibrium phase, which has a structure which is much different from that of the parent phase has to come out, it will have a lot of activation barrier. For example, if you look at the typical nature, if you take the supersaturated solid solution of aluminum copper, let us say 4% copper, and if it has to give you the theta phase, aluminum plus theta phase, for such a transformation to take place or for such a precipitation to occur, usually you have a large activation barrier. Though there is a large driving force also, but because the structure of theta phase is much different from that of the FCC, which is the parent phase, solid solution of copper in aluminum is nothing but the FCC phase. So from that, if the theta has to come out, it has a large activation barrier. Instead, the process will occur in a number of steps, finally leading to the theta phase. The first step is what we call the GP zones. Second step is called the theta double prime. In fact, I think I should have put another step here. So that is the final. So this is the third step, theta prime, and finally the theta. So this is how the transformation occurs in steps, and this is famous name people give, Ostwald step rule. Why does this happen this way? Is because the phases that are forming at an intermediate steps have their crystal structure which is similar to that of the parent phase, and as a result the activation barrier for these intermediate phases is much lower than the activation barrier for the final theta phase. So there is a continuous change in the structure from GP zones to theta double prime to theta prime and finally to theta, which is an orthorhombic structure. So there is a continuous change in the crystal structure. For example, GP zones we all know are nothing but copper clusters, which is nothing but an FCC. So when an FCC phase has to nucleate in another FCC phase, it's very easy, we know, because coherency can be easily maintained. As a result, you get what are called coherent precipitates. In fact, we call them as zones because they are so small to be even called as a precipitate. One cannot really see a clear boundary for the precipitate. How do we define a second phase? A second phase is that which has a definite composition and definite crystal structure and has a definite boundary to be distinguished from the parent phase. If the boundary is quite diffused, it becomes very difficult to call it as a second precipitate particle, so we start calling them as zones. So a small zone where the composition is completely different, but the structure is exactly the same. So it's again the copper structure, so it's copper having the FCC structure, so all copper atoms come together, form a small cluster, and that cluster is what we call the ZP zones, where some aluminum atoms are also there. It's not really 100% copper, but some copper with mostly it is copper rich with some aluminum in it. So such zones can easily nucleate in an aluminum matrix because their structure is exactly similar. So as a result, the activation barrier for its formation is much smaller, as you can see here. And then from there to the next step, which is the theta double prime, again some change in the structure takes place towards the theta phase, and again because now the transformation is not a large change but a small incremental changes that are taking place at each step, and as a result the activation barrier is not going to be very large in each step, and that's why the transformation occurs like this. But this need not have to happen in every system. There are certain systems where the transformation occurs in just one step. For example, if from an aluminum alloy, if Al3Fe has to come out, Al3Fe usually comes out in one step. There are a number of such systems. For example, aluminum silver is another example where the transformation occurs in just one step. So whether it occurs in one step or in a number of steps basically depends on how far away the structure of the product phase from the parent phase. If the structure of the product phase is largely different from that of the parent phase, then you see that it has to, because kinetically it is very difficult for the product phase to come out, so the system will choose an easy path for the transformation. So as a result it goes in a number of steps. For example, we have seen also in iron base alloys, when we take a martensite and start heating the martensite in steels, we know that the transformation from the martensite to the what is called the tempered structure does not happen in one step. The Fe3C does not come out in one step. First phase that you get is what? The epsilon carbide we call it, which is a hexagonal structure, and we know the Fe3C is basically orthorhombic. So from a BCT martensite or a BCC martensite, depending on how much is the C/A ratio, depending on the carbon content. So from that BCT martensite, which is a cubic, mostly cubic with a small distortion of C/A ratio. If you look at the C/A ratio in martensite, it's very close to 1.03 or something like that. It's not very large. So it's very close to the cubic. So from such a cubic structure, close to the tetragonal, so that's why we call it as BCT. From such a structure which is very similar to the cubic structure. In fact, we know that BCT is generated by the shear of an FCC structure, which is an austenite. So as a result, there is a clear one-to-one correspondence between the FCC austenite to the BCT martensite. So if you look at that kind of a structure and an orthorhombic FCC, orthorhombic Fe3C, so for that phase to come out is very difficult. So it goes by an intermediate step which is hexagonal, and we know hexagonal structure is very similar to FCC structure. So as a result, the formation of hexagonal epsilon carbide, whose carbon content in fact is higher than that of the Fe3C. Do you know what is the composition of Fe3, the epsilon carbide? Fe2.2C we say. So if you look at Fe2.2C, definitely carbon content of that is more than the carbon content of an Fe3C. That means that you need carbon atoms to come together in a small region by a larger amount for the Fe2.2C to come out, rather than if Fe3C has to come out. If the Fe3C has to come out, you need only less number of carbon atoms to come together in a small region. But then though we know diffusion wise this is a more difficult process, but the activation barrier for the nucleation of a new structure is so high that the system would prefer this process of a higher diffusion, higher amount of carbon diffusion. But we know that carbon is an interstitial element, so its diffusion is not really a major problem, particularly if you are doing tempering at around 300-400 degrees centigrade. At those temperatures, unless you are talking about really room temperature tempering, which is where carbon diffusion is very difficult, usually tempering is done at around 200, 300, 400 degrees centigrade. At that temperature, the interstitial element can easily diffuse, so you can definitely have a 2.2 C without any problem, and that is what happens in the steels. So you can see that there is a clear comparison between the aluminum alloys, what happens, and the conventional steels that we look at. So you can see this is how most of the precipitation in a conventional aluminum copper alloys goes. And when you add a small amount of magnesium to it, you get a new phase called Al2CuMg, okay, which is more stronger than the aluminum copper. So as a result, most of the aluminum copper alloys have some magnesium in it. The other conventional alloys are the aluminum silicon alloys, which we are all aware of. What is the most important application of aluminum silicon alloys? Castings. Yes, where do you use those castings? Engine blocks, correct. Most of the automobile engine blocks are all aluminum silicon alloys. There are two important reasons for it. Among all the aluminum alloys, aluminum silicon alloys are the ones which have very high castability or high fluidity, because they have a eutectic which is much lower. 577 is the eutectic temperature. So among all the aluminum alloys, aluminum silicon alloys are the ones which have very good fluidity. So they can be easily casted into any complicated shape. For example, if you look at an engine block, in most of the bikes nowadays, the engine block is visible from outside very easily, if you look at Hero Honda or something like that. So you can see the in order to improve the cooling process of these engine blocks, because they get hot, so there are a lot of fins on the engine blocks. So if you want to get those fins in a casting, unless the liquid has high fluidity, the liquid will not fill those intricate regions in the mold. So as a result, you really need a very high fluidity, high castability, which is what aluminum silicon gives you. But that is not the alone the reason why we use aluminum silicon alloys. The other major reason is their thermal coefficient of expansion is very, very low. For example, when you have a piston in an engine block which is moving continuously at high temperatures when the gases are generated, so you don't want the piston to expand and then jam the whole engine block. So you want a very low coefficient of thermal expansion, and that's what an aluminum silicon alloy provides. It is light, at the same time easily castable, and is strong because of the silicon. You know, the silicon is a very hard diamond cubic phase, and when you have this silicon in an aluminum matrix, you get a much higher strength. So that's why aluminum silicon alloys have good strength, excepting that one has to modify the silicon morphology to improve the toughness or the ductility of these alloys, because silicon usually comes out as needles in these aluminum silicon alloys. Where is silicon actually located in aluminum silicon alloys? Particularly if you look at the conventional aluminum silicon alloys, which are about 7% silicon or 12% silicon. These are the very common aluminum silicon alloys which we use in the engine blocks. Where is silicon in these alloys? Can you recall the phase diagram of aluminum silicon? Anybody? What is the eutectic composition in aluminum silicon? Yes. So aluminum silicon phase diagram looks something like this. What is the melting point of aluminum? 660, and this eutectic temperature is 577, and this is about 11.7%. And what is that of silicon melting point? Anybody remembers? 1410. So if you look at a typical 12% silicon, 12% silicon is usually about eutectic, because actually the eutectic composition in aluminum silicon alloys is only under equilibrium conditions it is like this. The moment you add certain alloying elements into it or add what are called modifiers, immediately the composition changes a little bit. That is why people usually give it as a range, 11 to 12%, something like that. So if you look at around 12% silicon alloy, it is usually a eutectic alloy, or if you look at a 7% silicon alloy, let us say 7% silicon, so it is usually a hypoeutectic. So in these two cases, eutectic and hypoeutectic, silicon is usually in the eutectic mixture. So that silicon in the eutectic mixture is usually in the needle form unless you do something. There are different ways of doing it. One way is to cool the alloy very rapidly. When you cool the alloy very rapidly, there is not sufficient time for the silicon to grow into needles, so it becomes like small, like as if you have chopped the needles, it comes out as small particles, and as a result you can have better ductility, because we know that whenever an aspect ratio of a precipitate is very large, aspect ratio means the length to the diameter or the length to the width, if that ratio, if it is very large, then the tip of these particle acts as what is called a stress riser, and you will have a triaxial state of stress coming out there, and because of which the material fails in a brittle manner. So you want to avoid such long needles in any microstructure. So that is another reasons why, for example, grey cast iron is so brittle, and that is the reason why people try to do what is called spheroidization and get SG iron or nodular cast iron, where you get nodules. So exactly in a similar fashion, so silicon in a needle form is not very good, so that is why we do either fast cooling or what is called modification. There are a number of modifiers people add, such as sodium, strontium. All these modifiers are known to be what are called surface active agents. So when you add a small quantity of these, we usually do not add more than about 0.02%, 0.03%. This is the range that we are adding. They are not really alloying elements. In a very small quantities that you are adding, that they really do not change the alloy characteristics much, but form a thin layer on the silicon particles which come out, or change the surface tension of the liquid in such a way that silicon particles do not grow but become spheroidized. So you get more or less spherical particles, fine particles. That is what you get. Another possibility is what is called, people have used some kind of deformation processes, such as warm rolling. That means you take this aluminum silicon alloys where the silicon is in the needle form and deform it to some extent at temperatures such as 200, 300 degrees centigrade or so. But that is not a real, frankly speaking, an advantageous situation, because you want to use aluminum silicon alloys as cast alloys, not mostly as wrought alloys. So as a result, once you make the casting, there is no question of again deforming that. So as a result, though a number of studies have been made by people, that has not become really popular, but the most important techniques is fast cooling, if you can achieve, and the modification. So these things give you a good modification, and which give you a good combination of strength as well as ductility in these aluminum silicon alloys. And in addition to this, if you want to add some precipitation hardening to it, people add a small amount of magnesium to it. Usually about 0.3% of magnesium is added to all the aluminum silicon alloys to give you what is called Mg2Si phase, and that gives you some precipitation strengthening in these aluminum silicon magnesium alloys. Other class of conventional alloys, whatever we are talking so far are basically the conventional alloys. The other class of conventional alloys are the aluminum zinc magnesium alloys, where you have Mg(Zn2) as a precipitate and gives you more or less good precipitation strengthening, but the most popular of all these precipitation hardening alloys are the aluminum copper magnesium, because the strength levels achieved are much higher. You get very good coherent precipitates in this. Then there has been a lot of work to develop newer aluminum alloys, which is what is the primary objective of our class today, is to look at what are the new alloys that have come up in the aluminum alloy series. One is what is called aluminum-lithium alloys. Still a lot of work is going on, and even in India, DMRL Hyderabad, a lot of people have been working on these aluminum-lithium alloys. The major interest in these aluminum-lithium alloys is in the lithium. Lithium is has an important characteristic. I think most of you know it. What is that? It is the lightest metal, not very light. It is the lightest metal. What is the density? Anybody remembers? It's 0.53. It is 0.53 is the density of lithium. So if you add lithium to aluminum, obviously you are decreasing the density. Particularly in aerospace industries, everybody wants to have the lower density, as low density as possible, because you want to have light alloys at the same time strong alloys. That's where lithium has another advantage, that lithium is also known to improve the Young's modulus of aluminum alloys. In fact, lithium is one of those few elements which dramatically increase the Young's modulus of aluminum. So you have a double advantage. On one side you are decreasing the density, on the other side you are increasing the Young's modulus. So if you look at what is called specific modulus, the specific modulus is much higher for aluminum lithium alloys than any other aluminum alloy. In fact, it is the highest specific modulus. That means modulus versus density. If you divide the modulus with density, you get the highest specific modulus and highest specific strength for these aluminum lithium alloys. Where from this is coming? This is coming again by a precipitation. And what is the precipitate? The precipitate that you have here is what is called AlLi, aluminum 3 lithium phase, which is called the cubic phase, L12 cubic phase. What is L12 phase? It's basically an FCC. It's basically an FCC structure where all the corner atoms are occupied by one atom and all the face centered atoms are occupied by another type of atoms. For example, if you look at Al3Li, Al3Li, you have 3 atoms of aluminum and 1 atom of lithium. So you can easily imagine that in a FCC kind of arrangement, lithium will go to the corners of the unit cell, and the aluminum will occupy all the face centered positions, and that's what is the L12 structure. And that is the phase which comes out in the aluminum lithium alloys, but that is not the equilibrium phase. The equilibrium phase in an aluminum lithium alloys is AlLi, equiatomic lithium, 50% lithium and 50% aluminum as far as the atomic percent is concerned, and because lithium has a very low atomic number, atomic weight, so as a result the weight percent wise, if you consider it, it will be much lower amount of lithium. So that is the actual equilibrium phase, AlLi, but this AlLi phase again has a structure which is not very close to that of the aluminum, and as a result its formation is more difficult. So when you take a typical aluminum lithium alloy with about 3% of lithium in it, usually most of the aluminum lithium alloys you have 2 to 3% weight percent of lithium. Aluminum copper alloys, what is the maximum we go? 4.5. Why can't you go beyond that?
So we come to the
Eutectic? Yes.
Did you extend the solver?
No.
The solver's line is near the solver's line. There is a melting.
Okay. What limits the maximum amount of solute in any precipitation hardened alloy?
Maximum solubility.
It's the maximum solubility. That's the crucial aspect. In any precipitation hardening, what is crucial is what is the maximum solubility. And in an aluminum copper alloy, the maximum solubility is about 5.5. If you look at the typical phase diagram of aluminum copper, it becomes very clear to you. This is the theta phase and this is the alpha phase, and this composition is 5.6%. So that's the maximum, but at the same time you cannot say I will make a 5.5% alloy of aluminum copper, because you can see if I make a 5.5% alloy like this, the solver's line is very close to the solidus line. If the solver's line is very close to the solidus line, when you are doing your solutionizing treatment, then there is a possibility that it can melt if your furnace is not maintained very well, with a high degree of temperature stability. If it is not there in the furnace, there is a chance that there is a melting, and once the melting occurs, then you cannot have homogenization. What is the basic goal of solution treatment? That you want everything in form of one single phase having a uniform composition, and that you want to quench it to get what is called a supersaturated solid solution. So as a result, one do not usually go beyond about 4.5%. That's more or less the maximum. So similarly in aluminum lithium alloys, usually about 3% is the limit that we use. And in such a alloy, if you normally cool it under normal conventional cooling conditions, you will get AlLi at the grain boundaries. You have in the solutionized condition, you have, let us say, all alpha, and if you start cooling it slowly, you will have the phase of AlLi coming out at the grain boundary. So this whole grain boundary is decorated with AlLi. This is a typical problem even in aluminum copper, we all know. If a aluminum 4.5% copper alloy, after solution treatment, if you do not quench it, if you cool it normally inside the furnace or bring it out into the air and then leave it there, what is going to happen? The theta phase, which is the equilibrium phase, is going to precipitate at the grain boundaries, because grain boundaries act as the nucleating sites. So it precipitates at the grain boundaries and forms a network of theta at the grain boundaries. So you have a brittle theta phase at the grain boundaries, and that's what makes the whole alloy very brittle. So this is the basic problem even in steels. When do you get this kind of a problem in steels? Yes, in case of hypereutectoid steels, you have the cementite network at the grain boundaries. When you are cooling the austenite, the cementite gets precipitated at the grain boundaries and you have the cementite network. You can see in most of the alloy systems, the criteria, the design criteria of alloy design criteria are more or less similar. So there also we do some treatment for spheroidizing those Fe3C, we call it spheroidization treatment. So similarly here, instead of doing spheroidization of this theta. In fact, if you want, one can do spheroidization of this theta, but that is not going to give you much higher strength. It can only make it ductile, because the theta phase is an incoherent phase. Because theta phase is an incoherent phase, because its structure is orthorhombic, which is much different from that of the matrix. So you are not able to get improved strengthening because of the just periodization of theta. If you want, one can hold it at slightly higher temperature for a long period. Any network kind of a phase will definitely become spheroidal, basically because surface area to volume ratio is decreasing. That is the basic driving force for any spheroidization, isn't it? So, but if you, instead of that, if you cool it fast and age it and get what are called coherent or semi-coherent precipitates, you can get a much higher strength. That is the basic philosophy behind the whole precipitation hardening. Otherwise, you would have been satisfied with just theta and somehow do some kind of a spheroidization treatment there. So similarly, in case of this aluminum-lithium alloys also, if you cool it normally, you get Al alloy. Instead of that, if you quench it and then do age hardening, you get the Al3 alloy precipitates. And here the precipitates are completely in the spherical form. This is another aspect in precipitation. What is the shape of the precipitate? The shape of the precipitate depends on what? The strain, which is called, what is called the misfit parameter. If, and of course the surface energy, interfacial energy, that is also crucial. So if you look at a precipitate which is coming out and measure what is the lattice parameter of the precipitate and know what is the lattice parameter of the parent phase, if the lattice parameter of the product phase is largely different from that of the lattice parameter of the parent phase, then we say the misfit is very large. And this misfit is going to decide whether you are going to get a coherent precipitates or semi-coherent or incoherent. Even if the structure is same, keep this in mind. Even if the product phase has the same crystal structure as that of the parent phase, if the lattice parameter of the product phase is entirely different from that of the parent phase, if the what is called the misfit parameter is more than about 20% or so, then you will definitely end up in incoherent precipitates or semi-coherent precipitates rather than getting the coherent precipitate. For coherent precipitates, you need the misfit to be very small. Now the question is, if you look at the strain aspect, if you have a spherical precipitate, in order to maintain the coherency between the matrix and the spherical precipitate, the strain generated is more when compared to a flat kind of a precipitate. If you have a precipitate in the form of a disc, let us say in the form of a disc, then the strain is much smaller because the coherency can be easily maintained between the matrix and the precipitate. That is why if you plot what is called the strain versus the shape factor, you will see the discs have the lowest strain and the spherical particles have the highest, and rod like particles, this is the disc, this is the rod like, this is the what is called spherical. So usually discs have the lowest strain. So every system would like to have disc type of precipitates usually, but at the same time a spherical precipitate has the lowest surface area to volume ratio, isn't it? So if you can have a spherical precipitate, you can have the lowest interfacial energy. So there is always whenever a precipitate is coming out of a matrix, there are two energies which are going to restrict the precipitation. There is one energy which drives the precipitation. What is that energy? Which is the driving force for the precipitation. If the precipitate has a lower free energy than the matrix, then you are going to have the precipitation, and that is the driving force. And this driving force is restricted by two positive contributions for the free energy. One is the surface energy, another is the strain energy. So the driving force has to be more than these two, so that you can have the overall precipitation. In thermodynamics we used to talk about this. So one has to minimize a combination of these two, strain and the surface energy. You can see the disc has the lowest strain energy, but if you have spherical, that will have the lowest strain surface energy. So how do you have a combination of these two? So that's where what is important is what is the actual misfit parameter. If the misfit parameter is very small between the parent phase and the product phase, then the system would prefer to have a spherical precipitate, because the surface energy can be lower. Already the misfit is very small. So if the misfit is very small, the strain is anyway going to be small, whether it is going to be spherical or disc. Definitely spherical is going to have a slightly larger strain than the disc, but if the misfit is very small, that means if the lattice parameter difference between the parent phase and the product phase is less than about 5% or so, in all such cases you end up in spherical precipitates. Aluminum silver is an example, and aluminum lithium is another example, that Al3Li always comes out as a spherical precipitate, whereas aluminum copper is an example where the precipitates are disc shape. Like that, so the actual shape of the precipitates depends on these two factors. One is the misfit parameter, another is interfacial energy. So as a result, as we can see, Al3Li is nice spherical precipitates. So you can see simply the situation is that you have an ordered FCC type of ordered. In fact, we should not call it any more FCC, as I have explained to you earlier. In fact, it is not really FCC, but we can say it is FCC based. It is an ordered structure based on the FCC. So you have an L12 ordered precipitates in an aluminum matrix. This is exactly similar to another high temperature alloy. Have you ever come across a very high temperature alloy which is used in aircraft engines? Superalloys, the nickel based superalloys. If you look at nickel based superalloys, what is the actual primary strengthening phase in a nickel based superalloy? It is called gamma prime. Gamma prime is the Ni3Al. You have an Ni3Al in a nickel matrix. So it looks like this, that if you look at the microstructure, you have a nickel matrix and spherical Ni3Al particles, and this is alpha nickel, solid solution of nickel with some other elements in it. Exactly similar situation you have in a aluminum lithium alloy, that you have spherical Al3Li particles with an alpha aluminum matrix. So this is the one which tells you that you can have very good strengthening. You have ordered FCC particles in an aluminum matrix, and you will also have sufficient ductility, because alpha aluminum is FCC, so good ductility, and the ordered particle is also the cubic ordered, not really tetragonal or orthorhombic. Cubic phases always have a higher ductility because of what? Where from ductility comes? Close packed nature of the planes and directions. Ductility is related to the slip, we know. If in any structure, if the slip can occur more easily, that particular structure is more ductile than any other structure. So if you look at the cubic structures, compare it with tetragonal type of structures, you can, or orthorhombic or any other low symmetry structures. The high symmetry structure, the cubic structure, has more close packed planes and directions, and because of which you have better slip systems, larger number of slip systems, and easy slip to occur. So that is why, in fact, I will show you a little later why in one particular system we want to convert a tetragonal precipitates into a cubic precipitate to improve the strength and ductility of the alloy. We will come to that a little later. So, this Al3 alloy seems to be a very good, but ended up into some problems. There was a lot of interest in these aluminum alloys for quite some time, and then slowly people started feeling that there are problems. One major problem is what is called shear localization. What happens is, the moment a dislocation cuts through this particle, if you have fine Al3 alloy particles, once a dislocation goes through this particle and cuts the particle, then all the remaining dislocations which are there go through the same path, and that path provides an easy path for the dislocations to move, and what you have localized shear taking place instead of shear occurring in a number of regions. So, you have localized shear, and this localized shear makes the alloy, reduces the ductility of the alloy. Those regions act as the crack initiators, and you have easy crack propagation taking place. So, in order to avoid this, people still tried some more additional methods. One of that is what is called addition of some zirconium to these aluminum lithium alloys. These are all just alloy design criteria, how to make the alloy stronger at the same time sufficiently ductile. What they did was added some kind of zirconium, and zirconium is known to react immediately with aluminum in an aluminum alloy and form Al3Zr. Al3Zr incidentally is also can be a cubic phase, again an L12 cubic phase, and this Al3Zr, when it is present in an aluminum alloy, and if you do solution treatment and quench it and start aging it, during this aging process, this Al3Zr acts as a nucleating site for the Al3 Li, because both are same structure. Al3 Li is L12, Al3Zr is also L12. So, as a result, you can have the Al3Zr on which Al3 Li nucleates. So, you have Al3Zr in the center and Al3 Li on top of it, and in a matrix of, let us say, alpha aluminum. And if you have this kind of a structure, and again you look at the deformation behavior of this kind of a structure, you will see that it is more difficult for shear localization to occur now, because you have an Al3Zr which is much more difficult to be sheared, because you have zirconium which is a very high melting metal. So, obviously Al3Zr has much stronger bonds, aluminum and zirconium have much stronger bonds than the bonds between aluminum and lithium, and as a result the breakage of those bonds is very difficult. For example, whenever you have to have a shear for the dislocation, the shearing a particular particle, you need to break the bonds of the two elements in that particle, and for that if the bond strength is much higher, then breakage of the bonds is much more difficult. As a result, the particles cannot be sheared. So, that is one of the advantage of this kind of Al3Zr. With that, people could solve to some extent this, but there are additional problems with lithium, is that the lithium is a very light element and very small element. So, as a result, there is a possibility of lithium being diffusing out of the aluminum alloy. If you make a aluminum lithium alloy component, hold it for a long period, people have observed that the surface composition is definitely depleted in lithium than the core of the alloy, because of the lithium diffusing to the surface and then getting oxidized with the atmosphere, because lithium can immediately get oxidized. In fact, we never keep lithium just like that. Lithium, sodium, all these elements cannot be kept outside, they are always kept under a protective environment. So, that can easily react with oxygen, and then you can have a loss of lithium, and then that provides a kind of a driving force for further lithium to go out, because you have a concentration gradient now, and if you have a concentration gradient, lithium can go. So many times one has to have some coatings on aluminum lithium alloys, so that one can prevent this kind of things. So there is a lot of research still going on how to use these aluminum lithium alloys and make best use of the increase in the Young's modulus that the lithium gives and the decrease in the density that it provides to us. Okay. So that's the type of work that has been going on aluminum lithium alloys. Then there are a number of other alloys which have come up. One is aluminum titanium alloys, and the aluminum iron vanadium silicon alloys, and a number of aluminum alloys where quasi-crystals and amorphous phases form. And some of these alloys have very high strengths of the order of around 1.5 or 2 gigapascals, which is much higher strength for any aluminum alloys. Usually an aluminum alloy such as aluminum copper alloy, it is very difficult to get more than about 300 MPa or 400 MPa, maximum could be about 500 MPa. That is the maximum strength that one can think of in conventional aluminum alloys, but a number of composites, nano composites are coming up nowadays with various kind of phases present, and those nano composites have much higher strengths. What are the various type of possibilities of nano composites? There are various types of microstructures that are feasible. I have just put down some of them, but there can be many more. One such thing is that you can have FCC aluminum grains in which you have very fine intermetallic compound particles, nanoparticles of intermetallic compounds. You will see some of the examples in what I am going to show you in future, and that is one type of. So, but here it is all crystalline. So, you have crystalline aluminum grains, and into which you have crystalline Al3Ta particles or any intermetallic particle. Al3Ta is one example. You can have Al3Ta, Al3Fe or any type of intermetallics, or nickel aluminides, for example. You can have aluminum matrix and nickel aluminide particles in it. So, or for example Al3Fe, Al3Li, if you can make it into nanoparticles, you can have Al3Li nanoparticles in an aluminum matrix, though not many people have tried that kind of a thing. Other possibility is that you can have an amorphous matrix, the second one, and into which you can have an FCC aluminum nanograins nucleated in an amorphous matrix. That means you make an amorphous matrix and crystallize this amorphous alloy. When you crystallize it, alpha aluminum comes out, what is called primary crystallization. We will talk about it a little more detail later. So, you can have different types of crystallization. One type of crystallization is what is called primary crystallization, where you can have FCC aluminum nanoparticles coming out. Third one possibility is that you can have an alpha aluminum matrix into which quasi-crystalline particles. As I told you, the first one is alpha aluminum matrix into which you can have crystalline intermetallics. You can have crystalline intermetallics, you can have quasi-crystalline intermetallics, depending on the type of alloy that you are choosing and depending on the cooling rates that you are choosing, one can have this possibility. One can also have another interesting thing is that you can have an alpha aluminum matrix in which the amorphous nanoparticles. How do you generate this? This can also be possible by, if you are cooling the liquid very rapidly. During this process, if alpha aluminum can nucleate as fine grains as dendritic alpha aluminum, the interdendritic regions are these, the liquid phase that you have. So, if these interdendritic regions, if they are very small, and when you are cooling it very rapidly, this liquid at the interdendritic regions can become an amorphous if the cooling rate is sufficient, and if its composition is sufficient to give you a good glass forming ability. So, you have already aluminum which has formed as dendrites, and you have interdendritic liquid, and this interdendritic liquid can undergo a glass transition and give you a glass, so that you can have the small pockets of amorphous pockets in an aluminum matrix. That can give you another possibility of mechanical properties. Another possibility is that you can have amorphous network in an with FCC aluminum. How do you get it? You can get again alpha aluminum nucleated in an amorphous matrix by getting initially either an amorphous phase and then nucleate a large number of alpha aluminum. For example, if you can somehow increase the nucleation rate of aluminum, you will have a large number of fine precipitates, and when you have so many fine precipitates, the amount of amorphous phase gets reduced and becomes a very small quantity, and that small quantity will remain at the boundaries of this aluminum, if you can imagine that. So you can have aluminum with a thin network of amorphous, that can give you additional possibilities of mechanical properties. All these kind of possibilities exist, and we will try to take up some of them and look at the real life examples of all these in the next class. We will stop.